Welcome to KT Semicon Self-Based Learning Module. In this session, we are going to discuss about Boolean Algebra and Boolean laws. So before that, let me share my screen. Now, in our Boolean algebra is nothing but it's a mathematics of logics, and it is one of the most basic tools which we use for analyzing and synthesis of logic circuits. And in Boolean algebra, we use these variables for representing our signals like A, B, or X, Y, Z, or M and N. And the Boolean values of a variable is either logic 0 or it may be either logic 1. And this 0 and 1 are basically Boolean constants. Now, this Boolean logic variable 0 or 1 is not used to represent actual numbers, but this is used to represent the state of the voltage variable, and it is also called as logical level. So, let's say if I want to represent a signal, let's say this is my signal, right? Now, if I want to represent this low signal level, then I can use logic 0 or Boolean 0, and for representing this high voltage level, I can represent it by using logic 1 or Boolean 1. And if we are representing our high voltage with logic 1 and low voltage with logic 0, this is known as positive logic. Now, in the case of negative logic, basically we represent high voltage with logic 0 and low voltage with logic 1. This is nothing but my negative logic. So, low voltage is basically represented with logic 0 and high voltage is basically represented with, low voltage is basically represented with logic 1 and high voltage is basically represented with logic 0. This kind of representation is known as negative logic. Okay, so depending upon what type of logic you are using, normally we use positive logic only. Okay, now after this we have something known as truth table. Now what do you mean by truth table? So basically a truth table is nothing but it's a relationship between your inputs and possible outputs of a logic device. Okay, and in the tabular form, so the number of inputs may vary from one to many depending upon the device or complexity of the circuit. Let's say if we are going to have a black box like this is my black box, and I have a set of inputs and a set of outputs for this black box. These are my set of inputs and these are my set of outputs. Now, a truth table is basically a table which is establishing the relationship between your input and output. So in the truth table, basically you're going to have inputs on the left hand side and outputs on the right hand side. So this is nothing but my truth table, a table which is basically establishing the relationship between your input and output is nothing but my truth table. By seeing the truth table, you can basically get the functionality of a particular design. Now, let us try to understand about basic Boolean operations. So, the very basic Boolean operation which we are going to discuss about this OR operation, AND operation, and NOT operation. Now, so we represent this OR operation with plus symbol and AND operation with dot symbol and NOT operation with either complement or exclamatory mark symbol or this symbol. Okay. So for example, if we want to represent this OR operation, then we are going to represent with this plus symbol. And if we want to represent AND operation, then we are going to use dot symbol. And NOT operation, we can represent either with this exclamatory or this symbol. Okay, or you can also represent with a bar. Now this symbol is basically used in coding. This is Verilog coding symbol, and normally we use it with bar. Okay, a bar. Okay, and this is also used in Verilog coding. Now let us try to understand about some theorems in Boolean algebra. So we have something known as complementation laws. So the term complements implies to invert, that is change 1 to zeros and zeros to ones. So let's say suppose if a is equal to 1, then a complement is nothing but 1 bar, that is nothing but it is 0. And let's say if a is equal to 0, then a complement or a bar is equal to 1. Now the complement of 0 is 1, that is 0 bar is equal to 1, and the complement of 1 is equal to 0, that is 1 bar is equal to 0. Now, if A is equal to 0, then A bar is equal to 1. And if A is equal to 1, then A bar is equal to 0. The double complement does not change the function, that is A double bar is equal to A. What does this mean? Let's say if A is equal to 0, then A bar is equal to 1, and A double bar is nothing but A bar the whole bar, that is nothing but 1 bar, that is nothing but 0. So A double bar is nothing but it is A. So if you apply double complement on a variable, then it is the same variable we are going to get. Next, coming to AND laws. Now, in the case of AND laws, again we have four type of laws. One is null law. Now, what do you mean by null law? Null law is nothing but A dot 0 is equal to 0. Now, we have one more law as identity law. That is nothing but A dot 1 is equal to A, not 1. Okay. And we have A dot A is equal to A, and A dot A bar is equal to 0. So the AND operation of a variable and its complement is equal to 0, and A dot A is equal to A itself, and A dot 1 is also A itself. Okay. Now, next we have something known as OR laws. Now, in the case of OR laws, we have again null law, identity law, A plus. Now, in the case of null law, A plus 0 is equal to A, and A plus 1 is equal to 1. So, many freshers confuse here. So, they simply write A plus 1 is equal to A. No, it is not. Here, A plus 1 is equal to A. A plus 1 is equal to 1, and A plus A is equal to A, and A plus A bar is equal to 1. And in the case of your AND law, A dot A bar is equal to 0. Next comes commutative law. So in the case of your commutative law, your A plus B is equal to B plus A, and A dot B is equal to B dot A. This is nothing but your commutative law. That means if you change the order of variables in OR and operations, the order is not at all important. You can basically change your order. Next comes your distributive law. So in the case of your distributive law, A into B plus C, which is nothing but AB plus AC. And A plus BC can be simply written as A plus B into A plus C. This is very important in terms of Boolean algebra simplifications. Next is idempotent law. So in the case of your idempotent law, A dot A so on A is equal to A, and A plus A plus A plus so on A is equal to A itself. Okay, this is nothing but my idempotent law. Next is De Morgan's theorem. This is a very important theorem. So basically De Morgan's theorem states that A plus B the whole bar is equal to A bar dot B bar, and AB the whole bar is equal to A bar plus B bar. This is nothing but my De Morgan's theorem. Next is principle of duality in Boolean algebra. Now, what do you mean by principle of duality is nothing but you are going to just simply replace AND operators with OR operations, and replace OR operators with AND operators, and replace 0 with 1 and 1 with 0. That is nothing but your principle of duality. And if you change this also, your Boolean expression or the equation remains valid. For example, let's say if we have a function f is equal to a plus b dot c. Now, the dual of the function is nothing but f is equal to a dot b plus c. This is nothing but my dual of a function. Next we have complement of a Boolean function. So the complement of a Boolean function involves finding the logical negation of the function. To do this, replace every variable with its complement and reverse all the operators using De Morgan's law for compound terms. And complementing a function flips its logic from 1 to 0 and 0 to 1. For example, let's say if I'm going to have f is equal to a plus b dot c, the complement of this f is nothing but a bar dot b bar plus c bar. So this is nothing but my complement of a function. Now, what are the complement properties is nothing but f bar plus f is equal to 1 and f dot f bar is equal to 0. I think this we have already seen in our AND laws and OR laws. So with this, we have completed this particular session, and in our next video, we are going to discuss about type of logic gates. Thank you.